Hi, my name is Malte Chlosta and I'm a PhD student at the Institute of Automation and Applied Informatics at the Karlsruhe Institute of Technology in Germany. Today I will give you an overview on an adapter-based architecture for evaluating candidate solutions in energy system scheduling. We need more renewable energy sources to limit global warming, but this raises challenges like volatile production. Using flexible distributed energy resources might cope with such challenges, but the scheduling poses complex optimization problems. The so-called Energy Hub is one exemplary simulation setup to study the energy transition. Conceptually, an Energy Hub is a unit that can convert, store, and condition energy carriers. The Energy Hub is a highly modular and flexible concept, and it's a promising candidate to support the local integration of renewable energy sources. We start by presenting the Energy Hub as a black box. An Energy Hub is always embedded in a so-called scenario. The scenario of interest today includes electricity and methane as energy carriers. The Energy Hub connects to the electricity grid, to renewable energy sources like wind and solar, and to a local industrial demand. The Energy Hub also connects to the methane energy carrier by connecting to the methane grid, again the industrial demand, and the biogas plant. The Energy Hub itself consists of 5 facilities that connect the two energy carriers bidirectionally. They include a battery, an electrolysis, a methanation, a gas storage, and a combined heat and power unit. Externally, the Energy Hub is represented as one combined unit that can be steered via one schedule. The optimal scheduling of separated facilities is a complex problem. To fully utilize the advantages of the Energy Hub concept, the scheduling concept has to be modular and flexible as well. But current scheduling solutions do not provide this. To motivate the shortcoming of current solutions, let's look at the typical scheduling solution for our Energy Hub implementation. On the left side, we see the different simulators from the previously introduced Energy Hub simulation. They are summarized as smart grid applications. There's one central client responsible for scheduling the Energy Hub, the so-called Energy Management System, or short EMS. The Energy Management System collects current states from the smart grid applications and uses them to generate schedules for all facilities. The process of generating schedules includes a client that handles the data, the EMS in our case, an optimization algorithm that generates candidate solutions, and an evaluation algorithm. Current scheduling solutions typically couple the EMS, optimization, and evaluation very strongly. This mutual coupling forms a rigid construct that is quite painful to adjust. This is problematic because scheduling approaches must support modular and flexible concepts like the Energy Hub. And the scheduling concepts must ensure functionalities for changes in the simulation system. Let's look at an example what the problem is. We remove the battery from our simulation system. The energy management system now has to manage the data from one less simulator. That's good. But the energy management system also now has to configure the optimization algorithm for a new problem which has one less degree of freedom. Same accounts for the evaluation algorithm. When we want to compare two optimization algorithms, the energy management system now has to know how to configure both of them, and it has to know which one to use. Those are quite difficult tasks, and they are quite separated from the actual data management tasks. So the coupled system becomes hard to extend and quite rigid. Literature supports our point of view by asking for more modular and flexible scheduling concepts. Our approach is to decouple the system into their respective tasks of data handling, evaluation, and generation of candidate solutions. For separation, we now make 3 categories. the client category, one for the optimization service, and one for the optimization algorithms. Clients might be energy management systems or controllers. Each of the three separated participants now only has one task. The smart grid applications measure states, the clients manage data, the optimization service evaluates and mediates, and the optimization algorithms generate candidate solutions. Clients now have access to the smart grid applications and manage their data. They then connect to the respective adapters in the optimization service and formulate an optimization problem. The optimization service then handles the optimization process with different optimization algorithms. Each algorithm is connected via one adapter. The optimization service is the mediator that provides flexibility and modularity through its architecture. An adapter-based design provides flexibility to the system in a sense that 1. Multiple clients can use one instance of the optimization service. 2. The optimization service uses multiple optimization algorithms. 3. The optimization jobs from one client can be split onto multiple optimization services. And 4. One optimization algorithm splits suggestions onto multiple optimization services. Let's look at the architectural structure to better understand how the optimization service handles this. We still have clients on the left side and optimization algorithms on the right side of the optimization service, with an adapter highlighted in blue. All sets of functions are marked in green and data classes in brown. First, predefined API functions manage the adapter's communication and mapping from external to internal data standard. 4 fixed data classes are implemented in the optimization service. First, the job data includes all setup information for the optimization algorithm and the metadata description of the optimization problem. The optimization results data class receives the final candidate solutions to hand it back to the client. On the optimization side, one data class interfaces candidate solutions. The evaluation results are then put back into the objective value data class. The data classes form a fixed interface that guarantees internal and external modularity. The internal processes rely solely on those data structures, separated into 3 parts: boundary conditions, domain mapping, and objective functions. One of the advantages is that the fixed data interfaces enable internal and external applications to be extended or exchanged separately. Another advantage of the modular approach is that some parts can be formulated generically. In our case, only job data, boundary conditions, and domain mapping implement domain-specific knowledge. We will have a look at job data and boundary conditions in more detail to understand the concept of domain-specific knowledge. A very reduced part of the job data class is the data model of converter units. Each converter unit can be described by a minimal power, a maximal power, a current power, and a ramp rate maybe. Each of the variables is marked as optional so that any level of detail regarding data modeling can be represented. A concise model is described by many variables, whereas a coarse model works with only a very few variables. Let's look at an exemplary boundary condition that relies on converter data. The power output of a converter is equal to the set point times the maximum output. So P is equal to S times P max. If the current power falls below a threshold P min, the converter turns off. That's like when you drive your car with 5 km per hour and you switch to 5th gear. Then it will turn off probably. We can rearrange the formula to directly condition for the set point S. because now the boundary condition directly applies to the domain in which the candidate solutions are generated. Boundary conditions always follow the same procedure. On first checking if all metadata exists. If not, they pass, but if it exists, the condition is applied. Similar to the data model, this generates independence to the level of modeling detail. We can implement many boundary conditions on a very concise level, and they will just skip if somebody inputs a coarse metadata model. More accurate data modeling results in more accurate calculations, but data models with little metadata still function. So now that we understand what happens inside the optimization service, we look at the implemented simulation system again. We have our EnergyHub simulation on the left, connected to an energy management system that now solely manages data. All 5 facilities inside the EnergyHub are connected, and some additional smart grid applications like a grid operator, a market simulator, or renewable energy sources are connected as well. The energy management system now connects to the optimization service via one adapter. The optimization service handles evaluation via very rudimental data modeling and boundary conditions. 2 different optimization algorithms are implemented. We have one evolutionary algorithm named GLEAM, which is specialized in scheduling of energy systems, and we have implemented a little debugging system, a Monte Carlo optimization, which randomly guesses schedules. The architecture now allows us to switch between them very easily. The grid operator provides us with a schedule, which is a specified load curve for the EnergyHub as one unit. And the scheduling problem is to control all 5 facilities in an optimal way to meet that one combined load curve. Specified load curve is represented in black lines. GLEAM's results are represented in green, and the Monte Carlo results are represented in orange. First, we can see that GLEAM manages to very adequately follow the specified load curve of the EnergyHub. In contrast, we can see that the Monte Carlo optimization does not notably differ from just randomly selecting values, even after very long run times, like 100 times higher than the evolutionary algorithm needed. The takeaway here is not that Monte Carlo should not be used for optimization, but that the architecture provides flexibility to exchange the optimization algorithms very easily. Let's recap. Current scheduling solutions lack the modularity and flexibility to adequately optimize the multitude of decentralized energy systems. With the presented architecture, we decoupled data management, evaluation, and generation of candidate solutions. This increased flexibility and modularity of the system. The separation of tasks eases further development through the definition and utilization of data interfaces. Some advantages, like the easy comparison of optimization algorithms, have been shown on a real case simulation system. Other advantages, like the possibility to scale the system via parallelization, need further implementation work. Future work will focus on the optimization service as a meta-optimizer. The optimization service has information regarding the optimization problem and holds access to the optimization algorithms, which makes it a perfect candidate to apply meta-optimization, or which optimization algorithm fits my problem best. A different topic of interest is to research what level of detail regarding data modeling and boundary conditions we actually need to adequately schedule energy systems. The implemented logic here was very rudimental, with only a few variables and around 5 boundary conditions. Yet for our example, we managed to adequately schedule our energy system. Thank you all for listening. Have a great conference.